First of all, thank you very much for inviting me to this to give a talk in this seminar series. I think it's a really great initiative that you have this going. Also, I think this is it was very nice to have the two first talks with Peter and Gianluca because a lot of or the models I'm presenting heavily relies on this type of work and new regional tectonic reconstructions. So my name is Eivind Straume. I work at Norse and the University of Bergen. I like the posters that I'm actually also affiliated with the University of Texas at Austin still, so that was correct. And the title of the talk is Impact of Mantle Convection and Dynamic Topography on the paleogeography of Arabia-Eurasia and the closure of the Tethys Seaway. And this work is I've done together with colleagues at UT and GFZ and Roma Trev, Thorsten Becker and Bernard Steinberger and Claudio Facena, which has been my main collaborators with this. So the Arabia-Eurasia collision is kind of the center of the Tethyan orogenic belt that goes from what we saw in the last talk, Mediterranean in the west, to the Himalayas in the east. And I'm not going to talk so much about the orogeny, but I'll talk about how this collision closed the Tethyan Seaway, which once connected the Atlantic and the Indo-Pacific oceans. So if we go back to, for example, the Paleocene, there may have been a situation, or there was a situation like this, where you had a deep oceanic connection between the Atlantic Ocean and the Indo-Pacific. And when this connection closed, it altered ocean circulation and presumably also climate, in addition to providing pathways for mammals to migrate between Arabia and Eurasia. And the current understanding is that this is of course hard to constrain, but the deep oceanic gateway closed sometime in the Oligocene, most likely, or late Eocene. And full closure is marked by the Great Old World Biotic Interchange, where you have fossil evidence of mammals crossing around 20 MA. And that provided a land bridge called the Gomphotherium land bridge. And it's proposed to facilitate this transition toward a stronger overturning circulation in the North Atlantic because of when you have an open gateway, you have less salinity difference between the Atlantic and Pacific, which promotes deep water formation in the North Atlantic. It's also proposed to have affected even the Antarctic circumpolar current by modifying this Tethyan Indian saline water that flowed south in the Indian Ocean. And the closure is also suggested to have influenced the south development of the modern day South Asian monsoons. So the part what I'm focusing a bit on today is that the evolution of or this closure is also linked to the deep earth and mantle convection through the signal of dynamic topography. So we have a global paleogeographic model which we have updated for the Arabia, Eurasia, and North Africa, and we've also done backward advection modeling of seismic using different seismic tomography models, converting to density, and use the same plate model as we've done for used for the paleogeography to reconstruct mantle density structures back in time and compute dynamic topography. But to zoom a little bit in on the study area, today most of the topography is generated by the collision. You can see the origin is in the north from the Mediterranean to the from the Alps to the Himalayas. However, there's also high topography in North Africa, which presumably is related to the far plume or upwelling hot material. The orange, no, the purple, pink arrows is present day GPS velocity, so you can see this collision is still ongoing. And the triangles are a volcanic compilation by Andrea Sembroni, which I'll talk a bit more about later. You can see the north of Africa, or the afar, shows very nicely in this residual topography plot, where you can see it's anomalously high, which is also seen in the seismic tomography here using TX 2019 slab, and at 250 kilometers depth, you can see the slow anomaly associated with the afar plume and the Red Sea rift. And on top of here is also SKS splitting indices, which gives an indication of mantle share, or presumably also mantle flow. So the idea is that there's a flow coming from the afar below Arabia towards Eurasia, and this may have been important for the closure of the shallower parts of the Tethys Seaway. So earlier this year, we published an updated version of this global digital elevation model for the Cenozoic, so for the last 66 million years. And this is based on these type of reconstructions, as we saw in the earlier talks, but there's several things we've done to try to get actual elevations. So I'm not going to go so much into the general modeling, but I'll go into the regional data used for the updates in the Eastern Mediterranean, Eurasia, Arabia section. So we use geological, stratigraphic, and paleo-environmental type of information to say something about the paleo elevation. And simultaneously, we also incorporate this in our plate tectonic model, and have tried to incorporate more recent kinematic reconstructions or elements from new reconstructions, such as the Van Hinsbergen model in the upper right. But we use the global paleomagnetic model of Torsvik and others, so we try to get in elements to make a more realistic case for the closure of the Tethys Ocean. And the product of this is maps such as these, which are digital elevation models for Arabia, Eurasia, and Northern Africa combined in our tectonic model. So we have these maps for times where we have data. However, there are a lot of steps in between or times in between where we don't. And in those cases, in the example of Arabia here, we use a blending routine to linearly interpolate between times where we don't have data to get a type of continuous model. And then incorporate this in the tectonic model to get the right locations. Using the plate model of Torsvik and others 2019, we used the backward advection routine of Bernard Steinberger, or I think first published in Steinberg and others 2004, with the updated seismic tomography and updated plate velocities to compute dynamic or paleodynamic topography. And these paleodynamic topography models are quite they're not too bad for very recent times, but going far back in time, they become increasingly less reliable. So we have to take them with a little bit of caution, and then try to compare our reconstructions, paleotopographic DMs reconstructions based on data with the model convection and dynamic topography. So number 4 here, you can kind of see the afar plume rising in the lower left of the profile. And then there's this finger of mantle flow flowing northwards, which influenced the dynamic topography, which is shown on the line on top. So this is model for shows our results from TX 2019 seismic tomography, but we can see the same type of pattern in all of the models tested, but it shows most clearly in this one. This northward migration of or northward mantle flow also fits with the volcanics of the region. So here we've reconstructed the data set compiled by Andreas Zambroni, which is essentially emerging data sets from Rabi and others and Hua and others, which where we plotted for each time step all volcanics dated within 1 million year of the time of reconstruction. So you can see when the afar plume arrives, there's a lot of volcanism in the Horn of Africa, and then it migrates northwards towards present-day Israel, Jordan, and it kind of comes to what's known as or what's called the Mesopotamian Trough, which is this shallow ocean passage between across Arabia, between the Proto-Mediterranean and the Indian Ocean, around the time where this land bridge is supposed to have occurred. So it fits quite well with the closure of the shallower part of the Seaway.
Eivind, you're at 11 minutes now.
Okay. So what we propose with our with this new reconstruction is that it was more like a two-step closure of the Tethys Seaway, where the deeper oceanic part closed before the shallower Mesopotamian Trough. And the Mesopotamian Trough closure correlates or is when you get this Confotarium land bridge around 20 MA. And the first closure is likely the one that has the most impact on regional and global oceanography, while the later could have an impact on still have an impact on larger scale ocean circulation, but it's less clear from a variety of modeling studies showing different results. And to summarize a bit, the afar plume upwells and northward mantle flow caused the uplift and then biodynamic topography, which closed the shallower part of the Tethys Seaway and enables or influences the timing of the Gonfotarium land bridge and the Great Old World biotic interchange. So the suggestion is that this makes this shallower part close earlier than it otherwise would have by the collision itself. Let me see. Yeah, so to summarize, progression of the positive dynamic topography signal fits well with the northward progression of volcanism from East Africa, far plume. Also, uplift records from Ethiopia, Israel, Jordan, and Eastern Anatolia seems to fit well with this northward progression, which is plotted here in the mid panel, and the triangles show recorded uplift from the Ethiopian plateau, Israel, Jordan plateau, and Anatolia plateau. And then changes in dynamic topography and volcanism was likely important in establishing this Confotarium land bridge and control the timing of this appearance, and then also one of the greatest faunal migrations of the Cenozoic. Thank you very much for listening.
Thanks a lot for this last talk, Eivind. There's time for questions. I would have one, as usual. In how far does the rifted margin north of Arabia affect the closure of the Seaway? Because it's not there anymore. How much knowledge is there about this type of the margin, and how much uncertainty does that induce?
So I think it's quite a lot of uncertainty. We've used the COB of the Van Hinsbergen model to reconstruct the Arabian margin, and that of course extends or extends further in, or makes Arabia greater than it would have if you use like the present day or like Earth-Byte model, for example, or the seed model. But if that's enough to or if it actually accounts for the northward extent, it's I suppose quite uncertain, and it matters of course for when you have the closure of the deep seaway in our model, and if it were significantly further north, then the collision would happen sooner, and you would close the deeper part sooner as well. So that's I don't know to what certainty the Van Hinsbergen model has that COB, but I suppose it's quite uncertain. And yeah, a potential source of error.
Okay, thanks. Peter has a question.
Yeah, very nice talk, Eivind, and nice animations. Maybe a general question to this. Would you use your approach maybe also in a setting where you're not closing an ocean, but opening an ocean, for example, the Northeast Atlantic, because you have a similar setting in the way that you also have blue. You might also have a contribution about dynamic topography, and I think also that's what people are really looking at, is the paleogeography in this area, because I think we at least don't really know when the opening, when there was the seaway opening in the Northeast Atlantic. So could you use your approach to model it in an opposite way to look at when does the ocean open?
Yeah. So we have done, or I have spent some time in with this in the North Atlantic. So the previous update before the Tethys was or when this first was, we made this model was with a focus on the Northeast Atlantic and the Atlantic Arctic oceanic gateways. And because then you have the influence of the higher crustal thickness of the Greenland-Scotland ridge and the dynamic influence from the Iceland plume. And this type of approach with the backward advection kind of would be great, but it's you lose information back in time of upwellings because they're backward advected down in the mantle, and if that's been going on for some time, the model doesn't know that. So what we did for Iceland in the previous model is to there's these temperature estimates based on these V-shaped ridges that straddles the Reykjanes ridge, where you may have had these pulsations in plume temperature in the Iceland plume, and then just make like a Gaussian shaped swell around Iceland, and alter the supposedly dynamic topography, or alter the present day signal based on the temperature fluctuations. And that's of course kind of a crude approach, but you would at least get some variations on the ridge based on the Iceland plume, and also it's more, I would suppose, more realistic than not having it, because then you will get very deep gateway. So yeah, but that's of course room for improvement there too. But we at least this model compared to many of the other Paleo-DM models for the Northeast Atlantic, I would say is at least quite reliable, because it's common to exclude both Iceland and the Greenland-Scotland ridge, so you get like a 4,000-meter deep ocean all the way to the Fram Strait. And then for the Fram Strait, I didn't do that much, but include like these microcontinents and made some use the present day residual signal of the microcontinents and also this Greenland ridge to add to the, because we reconstruct the bathymetry using these age depth curves, and then add some extra topography based on crustal thickness or the present day residual. So but yeah, it's these are large scale models, so the very fine details are sometimes lost. But hopefully, with some time, we can improve them for or constantly improve them.
Yeah, I think that would be maybe also combining. If not sure if the approach that we develop would help or give a finer constraint. That I see
It
a link
would
in both sides.
definitely help
I see a link in both
for
sides, right? Because we're also interested in the paleogeography, but currently the model we have does not really. I don't have information this yet in my model.
So for the continental margins, for example, it would be great to have because I have static COBs that doesn't really incorporate any stretching, and I remove sediments from the margins, but it's like higher detail in these tectonic reconstructions would really make the model, like the topography models, much more reliable.